thank the organizers for asking me to do this and thank the audience for showing up for these lectures. I hope some of it is of interest. So what is the Grothendieck-Riemann-Roch theorem is something which is a serious application of intersection theory, which is the main theme of this workshop. So it's about several different things, but Grothendieck-Riemann-Roch fits well in it. So I want to start by giving you some background. What are the standard Riemann-Roch theorems you might have encountered? For example, if you looked at Hartshorne's book in algebraic geometry, there is a Riemann-Roch theorem for curves. There's a Riemann-Roch theorem for surfaces, and so on. Why do those things have anything to do with intersection theory and the like? That's let me start by giving some background remarks. So background. So first of all, let's look at Riemann-Roch for curves. So here the context is the following. Let X be a non-singular projective curve over our ground field K, which I'm going to assume is algebraically closed. In my lectures, I'll basically work with varieties or algebraically closed fields. It's not important for everything, but doesn't matter. To get the general picture of how things work, this is fine. If you're interested in the most general things, you can only look at the book and try to, look for minimal hypotheses. So I'm assuming the ground field is algebraically closed. Then there's the notion of a divisor on such a curve. So what's that? That's some formal expression like this, nj times xj. So this runs over a finite set. I don't specify how many j's there are. Any finite number will do. And these nj's are some integers. And the xj's are points of x. So it's a finite formal linear combination of points with integer coefficients. That thing is called a divisor. So Riemann-Roch theorem on a curve takes such a divisor and tries to tell you something about it. So associated to such a divisor, I have various things I can do. I can look at its degree. You just take the sum of those coefficients nj, and this is some integer. That's the degree. Okay. Then another thing which I have associated to the divisor is what's called its support, which is just take all the points xj, whatever they are, which appear here, and when I have nj here, I want not equal to 0. So you want to be very pedantic about it. Finite set could have been the empty set. That's also okay. Then I get the divisor 0. I don't take any points and don't have any coefficients. That's allowed. But if I have points at all, then I'm assuming the coefficients are non-zero. So every xj occurs with some coefficient. So the set of xj is the support. Okay, just to be pedantic. Okay. So this is some finite subset. Okay, so if I have this divisor, I have these things associated to it. I have something else more sophisticated. I have OXD associated invertible sheaf. So how do I give this sheaf? If I have an open set U, Zariski open in X, well, I'm over some general field. I suppose there's no other reasonable topology right now except the Zariski topology. But if the field K was the complex number of real numbers, there's another topology. So I should be careful. I'm talking Zariski open sets. So what is this? This is set of all f such that f is a rational function on x, and one more condition holds. I forgot here, I should have done something. Since anyway, you've got the notes, I can do things in a different order. If I have any one of these xj's, then associated to it I have a local ring. Can you see if I write here? Is that okay? OXXJ, the local ring at the point, right? And now X is a non-singular curve, so this local ring is a discrete valuation ring, right? It's an example of a discrete valuation ring. So in particular, it contains its maximal ideal, which is a principal ideal. Okay? So I have this data also associated to each of those points xj. So when I want to write this sheaf and I want to tell you what the sections are on an open set, I need this information here. And one more condition, for all and one, f is a regular function, it has no poles of zeros, on u minus the support of d. And 2, if xj belongs to u for some j, then t raised to the power nj, where nj is this coefficient of xj, t to the nj times f belongs to the local ring OXXJ. That's the condition. So I can write this condition similarly, i.e. f belongs to OXX for x in u minus support t. I can write the condition in a similar fashion. T raised, the corresponding tx raised to the power 0, so to speak, is the coefficient. Right? So this defines the invertible sheaf. So then what does Riemann-Roch for a curve tells me? For x, for d, says, well, there are many ways you can write Riemann-Roch. I'll write it in a particular way, which is somehow appropriate for the generalization which we want to go to go towards later on. So the formulation I thought is good to write. Yeah, I should have said here, I've got this invertible sheaf, then therefore I have things like HIX OXD is cohomologies. So these are finite dimensional vector spaces, K vector spaces, and I also know that HI is equal to 0 unless 0 less than the I less than or equal to 1. The only possible non-zero HIs are the H0 and the H1. That's somehow because X is a curve. And so these are properties I know. So then I can look at chi x OXD is summation I greater than or equal to 0 minus 1 raised to the I dimension over K HI x OXD, which is of course just dimension H0 OXD minus dimension H1 OXD because of that vanishing property. But in any case, it's an Euler characteristic. So what does the Riemann-Roch theorem say? It tells me something about this. So then the theorem says chi OXD, chi x OXD is equal to the degree of D. Well, one way of saying it is 1 minus G, where G is the dimension of H1 x OX equals what's called the arithmetic genus. This is the most standard way you would see it in the book, but I want to view it a little differently. I want to write it like this: degree D plus half the degree of C1 of the tangent sheaf of X. this is really the formulation which is better when we want to think of the Riemann-Roch formula, the general Riemann-Roch theorem. I want to think of the same thing like this. So what is this? This involved some new things here, Tx and C1. So Tx is tangent sheaf of x, which if you, for example, you looked at Hartshorne's book, you have the sheaf of scalar differentials of your curve x, non-singular curve x, and take its dual. Dual of dual OX, or I should rather say OX dual of sheaf of scalar differential. Right, that's called the tangent sheaf. And there's a direct definition of the tangent sheaf in terms of derivations and so on and so forth, which I won't go into right now. For example, the fibers of Tx at points would be what are called the Zariski tangent spaces at the points. So you have this tangent sheaf, but then you have this C1. So what is this C1? So C1 Tx is supposed to be something lying in Chow 1x. The Chow group of codimension 1 algebraic cycles on x, but x has dimension 1, so codimension 1 is saying dimension 0. So another way of writing it is Chow lower 0 of x. So remember, when we have these so-called Chow groups, and you have been studying them in the intersection theory, for general x's, you often in the standard theory work with Chow with a lower index, which is Chow homology or whatever, and x can have singularities and so on and so forth. And then you have these Chow with upper indices, which are some kind of operators. I guess that must be the way it's been done. And if x is non-singular, one of the theorems is that there's an identification of the two. And I'll later on use the explicit form of those identifications, but let's say, x is a non-singular curve. I have Chow upper 1x, which is the same as Chow lower 0x. And let me just remind you what this is. So it's sort of, it is, let me say it like this. Z1x mod R1x, if I write it in codimension formalism, Z1x in dimension formalism would be Z lower 0x equals 0 dimensional algebraic cycles, which more abstractly is just a free abelian group on points, closed points, I want to be very careful, which has a more classical name, group of divisors. Right? And what is this R1? Let me remind you again. Well, since I've identified in the end the group of cycles which is divisors, there's a notion of linear equivalence of divisors, a classical notion. So R1x is divisors linearly equivalent to 0. And then we have a map Z1x to the integers, which an element of is just one of those divisors nj xj, and then I had a map sending it to summation nj, the degree map. It's a fact that degree in fact descends to give a well-defined map degree from Chow 1x to the integers. There's a well-defined map. In other words, if something is linearly equal to 0, the total degree of such a divisor is 0. These are all classical facts. Sorry? Yeah, sure. My lectures several things I'll do will overlap quite a bit with things which other people did, but it'll overlap, I think, in a sense of definitions, and maybe I'll write properties, but any non-trivial proof which overlaps with earlier material, I'll say, you've seen already the proof of the following difficult fact, and then leave it to you without any. So, but it's good to review everything and just see where it fits in, and in particular, which are the things which go into growth-centric Riemann-Roch. If you want to see that, that's sort of what I'm trying to do. Anyway, yes, so I have this, and somehow, I haven't still explained from my point of view, though again, I believe people have done it last week already in some fashion. What is this C1? So, here, the point is that there's a map from pick X to chow1 X with the fact that if I take any L, it's an invertible sheaf, then any such L is isomorphic to OXD for some divisor D. I mean, there may be many Ds which have this property, but every L occurs in this form. OXD is an example of an invertible sheaf, and the theorem is every invertible sheaf is isomorphic to some OXD, perhaps many such OXDs. So then what you do is you take the class of such an L, choose a representative OXD and associate to it the class of D in the divisor's mod linear equivalence. Right? There's such an association, because you know every invertible sheaf is isomorphic to some OXD, I can choose one and do it, and the assertion is it's well defined. I'm not proving it, this is all part of the theory, but I'm just trying to formulate things in a particular way. Okay? And a further fact, this map from pick X to chow1 X is in fact an isomorphism. The two line bundles are isomorphic if and only if the corresponding, if for each one I choose a divisor representing it, the two divisors are equivalent. So once it's isomorphic, there must be a map, right, this isomorphism I called C1. So I have an invertible sheaf, there's this map which associates to an invertible sheaf or divisor class. That map is an isomorphism. I call it C1. It's just a definition. And in fact, the general theory of Chern classes also, as far as I remember, and I think even whatever you people have done in your course, somehow you'll use something like this to talk about C1. It's the other Chern classes which you construct by some various methods. For line bundles, you have to be sort of given it directly in some fashion. And this is a feature of many of these things in the theory of cycles. Even if you want to construct Chern classes of some kind of objects, bundles of some kind, with values in some kind of theory of some functor on schemes or diagrams or whatever it is, always the line bundle case you must do directly in some fashion, using the functions defining the local divisors or whatever, from the construction of your theory, whatever it is. And then the higher guys, higher Chern classes, are somehow produced by the machinery, the homological algebra and the geometry. Okay, so here too we see this feature. Well, one element here is the class of the tangent sheaf. Since X is a non-singular curve, its scalar differentials and therefore the dual do form, give me an invertible sheaf. There must be some divisor associated with it. There are lots of them. Choose any one, take its class. The class is well defined. That's C1 of the tangent sheaf. So in this formulation this way, that's what this means. Notice here there's a half. So because this is always an integer, I get the fact, which is not obvious to me directly, that C1 of the tangent sheaf, the degree of it is an even number. So these kinds of things will come up even in the other theories, the later parts. So I think this is basically what I want to say. Oh yeah, right. Now Riemann-Roch here I said it for OXD. What about for an invertible sheaf L? So if I write chi xl, where L is invertible, now I can write it like this. I can think of it as degree of C1L. Instead of writing degree D, I take degree of C1L, which is a class, and the class has a well-defined degree, plus half degree of C1 of the tangent sheaf of X. Now the right side has two places it has C1. One is C1 of the sheaf whose chi I want to compute, and the second is C1 of the tangent sheaf, which is something intrinsic to the space X. So those are the features I want you to remember from this, and here somehow I got a denominator. Still further I can go, I can take F, a coherent sheaf of OX modules. It too has cohomologies, they're finite dimensional. I can talk about a chi for such objects also. And Riemann-Roch can be formulated for that also, chi xf So now what will be the formula? It will be degree of C1F. You have to figure out what this is. So part of the theory, when F is some general sheaf, what is this C1? For line bundle, I did something. For a general F, you have to think. Plus, and now I'll get another term, rank of F times half degree C1Tx. So this is the most general Riemann rock you can write on a curve. So now this has, in addition to this Chern class, which here is okay, but here we have to understand it better. We have not yet done it. This is still what it was, and then there's this additional thing, rank. Why should rank appear? That's very reasonable. One example of a coherent sheaf is you take a bunch of divisors and take the direct sum of those invertible sheaves. Chi adds up, the right side better add up. For each of those divisors, I write the Riemann rock like this and then add up all the terms. Of course, as many summands as there are, I'll get that many terms this constant. So rank coming there is very reasonable. Okay. So fine, this is Riemann rock on a curve. Now what about a surface? That too is there if you've studied Hartshorne, for example. He has a Riemann rock theorem for surfaces. So the Riemann rock theorem I'm going to write down is slightly different from what he writes, though of course it's equivalent. The X is a smooth projective surface, let me say. Okay, then let me assume K is algebraically closed for simplicity. Then I can talk about D, a divisor. So what does such a thing look like on a surface? It's sum over J, a finite set, Nj, some integer, but now instead of points I have curves. So a divisor on a surface is a finite formal linear combination of irreducible curves on the surface. Well, divisors are some kind of codimension 1 cycles. So this is the group of divisors is otherwise called Z1X equals a group of algebraic cycles of codimension 1. And then we again have a Chow1X, which is Z1X mod R1X. So this corresponds to linear equivalence, divisors linearly equivalent to 0. I still have invertible sheaves associated to such divisors. I won't try to write down directly the sections. It will be given by functions. Sections over some open set would be the functions whose poles and zeros are governed by these coefficients nj. But if you think carefully, I mean that condition sort of makes sense at the generic points of the CJs. If you want to use the scheme language where I do have discrete valuation rings and I can argue exactly like I did with curves. But on a surface, you have to argue a little more. In the codimension 2 points, what happens? How do you find the sections? There, because the local rings are regular local rings, which are UFDs, somehow things patch themselves together nicely. There will be a unique way of extending nicely to the codimension 2 points. Let me not get into the details there. It's part of the theory. So because X is a non-singular surface, if you specify what happens in codimension 1, the codimension 2 stuff automatically somehow takes care of itself. Okay? If you want to be very fancy, every regular local ring of this kind, let's say occurring in geometry, or probably any regular local ring occurring anywhere, is the intersection of its localizations at the height 1 primes. That will be the commutative algebra fact behind things. So you want to check whether a section is a section of the line bundle at some point. Does it lie in the stock at some point? That's a free module of rank 1 over some local ring, and I can check whether something lies in the stock or not by checking it by localization, further localization at height 1 primes. That's what's involved behind this. So I have associated invertible sheaf. Then I can again talk about its cohomologies, HIX, OXD. These are again finite dimensional. Okay. And vanish unless 0 less than or equal to I less than or equal to 2. Because X is a surface, the dimension is 2, only the zeroth first and second cohomologies could be possibly non-zero. And so I have that, and so therefore again I have a notion of chi x OXD equals some I greater than 0 minus 1 to the I dimension HI x minus Euler characteristic. So what does the Riemann-Roch theorem say? It gives me a formula for this, just like before. Here I had, I erased it. Well, I have versions of it here. The Euler characteristic of this invertible sheaf was given in terms of Chern class of invertible sheaf, the Chern class of the tangent sheaf. Here it will be similar, but more complicated. So Riemann-Roch would say that chi x OXD is equal to degree of C1 OXD dot the sum C1 OXD plus C1 of the tangent sheaf divided by 2. But there's another term plus degree of C1 of the tangent sheaf of x squared plus C2 of the tangent sheaf of x, and the whole thing is divided by 12. So this is one version of Riemann-Roch for a surface. Now the Riemann-Roch which you might have seen in say something like Hartshorne's book, if you looked at chapter 5 in Hartshorne's book, looked at Riemann-Roch for a surface, he'll have things somewhat like this. Here he would have written, instead of this strange term, he would have written the chi, the Euler characteristic of the structure sheaf, of the sheaf OX of function. And here maybe he would have written the canonical divisor and he would have written a minus. So that's fine as far as classical geometry is concerned. But from the point of view of growth and Riemann-Roch, this is the way I should be thinking. I should be using only the Chern classes of the sheaves in question and the Chern class of the tangent sheaf and write some expression. So what type of expression is this? So first of all, what is this C1? Again, there's a chow1 x. I can do it like this. I can take it this way. This is what I should have done for curves, and as I did in the notes, but trying to do it off the top of my head, I inverted it. There's a natural map going this way, which sends the class of divisor D to the class of OXD. And the assertion is this is an isomorphism. So of course there's an isomorphism the other way. And this inverse isomorphism I call C1. So it's got the same description as before, that given an invertible sheaf, it's possible to find some divisor D such that the invertible sheaf is isomorphic to OXD, and the class of that D in chow1 is well defined. So that's the so-called first Chern class. So that takes care of this. This is also fine. It's not, I still have, even though X is a surface, I can talk about its scalar differential. This is now locally free of rank 2. And then I can talk about Tx, the dual locally free sheaf, the so-called tangent sheaf. Okay, this is again some locally free sheaf of rank 2. But now because I'm on a surface, there are chow groups, chow upper 1 and chow upper 2. There are 2 of them. So, for example, there's the possibility of C2 of a rank 2 sheaf. So this is a new type of thing which I put on a surface. The rest of the stuff, how does it look? Here is, there are two C1 terms. So both of these are in chow upper 1x. So the sum of them lies here. So I'm taking two elements of chow 1x and multiplying them. So dot, first term, uses chow 1x cross chow 1x to chow 2x, which I've written in the form A dot A B goes to A dot B. That's the way I've written this dot here to mean the intersection product. So here I'm starting to do intersection theory. I have two divisor classes and I'm intersecting them. Right? So that gives me an element in chow 2x. So chow upper 2x, x is a surface. That's the same as chow lower 0x, which is the same as, if you like, well, let me write it like this time. Z0x divided by R0x. Z0x is the free abelian group on points. R0 is some equivalence relation, the rational equivalence. So these things are called zero cycles. Zero dimensional cycles or zero cycles. And then I have a notion of rational equivalence, which has been developed in general earlier in other lectures. And I have the quotient. Notice that there is a map from this again to the integers given by the degree, which on the free abelian group on points is the earlier map. If an element here is just some linear combination summation nj xj, and I map this to summation nj, and the fact which needs proof, but is part of the theory, is that this homomorphism which is defined on the numerator, in fact passes to the quotient. So there's a well-defined degree homomorphism to the integers. So anytime I have an element in chow 2, I can speak out its degree, which is an integer. So that's what this is doing here. Here's an element of chow 1, here's another element of chow 1, intersect them to get an element of chow 2, take the degree of that, divide the degree by 2. That's what that's saying. So in particular, that degree better be an even number. Well, we have to think a little bit about that. And then the second thing is like that. I have the first Chern class of the tangent sheaf, square it. That makes sense. Then I'm adding another class in chow 2, which is C2, the second Chern class. So somehow I have to make sense of Ci of Tx in chow Ix. I believe Chern classes have been defined in some fashion already in the course, right? People have discussed it. But in any case, that will be an example of that. And then this is a zero cycle, and I can. And here I have this 12 in the denominator, this strange looking thing. So notice now, if we have a formula like this, put d equals 0. Then this term sort of disappears because C1 of the trivial bundle is supposed to be 0. C1 is a homomorphism. So then I get that this thing is the chi of the structure sheaf, the Euler characteristic of the structure sheaf. So I get the non-obvious fact that if you take C1 squared of the tangent sheaf and add C2 and take the degree of that cycle, it is always divisible by 12. And in general, a similar thing in a higher dimensional, something will be divisible by 720 if I remember right, in dimension 4, and so on and so on. Various strange divisibility things come out of it. Anyway. So the Riemann-Roch formalism produces these formulae for chi. The shape of the formula is like this. So let me now briefly say what the next step is, which is the Hirzebruch Riemann-Roch formula. Oh, maybe for a surface I should say what it is for a sheaf. Yeah, that's also not without interest. So F is a coherent sheaf Then I have several things associated with it. First of all, since it's no longer necessarily an invertible sheaf, I have its rank, which is some positive integer basically, unless f is 0. Then I have Chern classes CIF. And now in general, I could be 1 or 2. For example, F could be the tangent sheaf. It had a C2, right, that appeared in the formula. So general sheaf F may have a C2. The earlier Riemann-Roch which I wrote here for OXD Luckily, OXD is an invertible sheaf. There is no C2. C2 is 0. But for a general sheaf, there will be a C2. For example, the tangent sheaf usually has a C2. And in fact, C2 of the tangent sheaf of the surface, if I remember right, the degree of that is the topological Euler characteristic of the underlying surface, if, for example, you have complex numbers. The top Chern class of the tangent sheaf is something very interesting. The degree is some interesting thing. So it's certainly not 0 and general. So what's the general Riemann rock? It will look like this, chi xf. I'm just trying to give the shape of the business. C1f multiplied by, this part looks like before. Rank f times this range. And then I have another term here. This is the general form. So it involves C1f as well as C2f. All the possible intersections you could think of. You have C1 of the tangent sheaf, C2 of the tangent sheaf. You have C1f, C2f. You have rank f. Every possible one is there. Every possible intersection I could form to get a 0 cycle, there's a term. Okay, and with some coefficients. That's Riemann rock for a surface. The next in the development of Riemann rocks is something called Hirzebruch Riemann rock. I don't want to write down exactly what it is in detail. We'll come to those things later. Anyway, when I do GRR, you'll see this is a particular case. But what is the shape of this thing? So the idea is X is non-singular projection. For simplicity, F is, let's say, a coherent sheaf. And I have Tx is tangent sheaf. Then I have things like the Chow groups. And in particular, if I have Chow in the top degree, there's a degree homomorphism. This is the same as Chow lower 0 x, which is z0 x mod r0 x. So this comes with a degree homomorphism. So these are general features. You have Chow groups, and then you have a theory of Chern classes. So CIF belongs to Chow IX, and similarly Ci of Tx also belongs. And then of course I have the rank F. Belongs to natural numbers. So these are all natural invariants I can write down. Then I can also observe that if I have some positive integers r1, r2, rs with summation rj equals, let's say, d equals the dimension of x, under these conditions I can write an intersection number. If I look at Chow R1x cross Chow RSX, I can use the product structure in the Chow ring. So product, so let me say intersection product. Which will go to Chow dx, where d is a dimension. And then there's this degree which went to the interior. So this thing is called the intersection number. And so if I have any indices R1 to Rs such that the Rj's add up to the dimension of the space, and if I have Chow classes in each of those particular codimensions, I can form their intersection product and take the degree and get a so-called intersection number. So what HRR will do, it will give us a certain, there exists a universal polynomial Pn of x0, xn, y1, yn with rational coefficients such that if we view the polynomial algebra as graded over Q adjoint x0 with degree xi equals degree yi equals I. So take a polynomial ring in two n plus 1 variables and take an element in it. The 0th variable x0, I don't give any degree at all. The other variables I give degrees. Degree of x1 is 1, degree of x2 is 2, and so on. Degree of xn is n. And similarly, the y's have degrees up to 1n. So you have this situation. So if I use these degrees, it makes sense to say some polynomial is homogeneous of degree n. Then this Pn is homogeneous of degree n. And secondly, chi xf can be written as degree of Pn of rank f C1f CNF C1 Tx Cn Tx. Pn depends only on n and not on, it's some universal polynomial in that sense. For each dimension n, there is a polynomial Pn. It is homogeneous of degree n in this weighted sense. X0 doesn't count at all, the weight, but the other xi's, xi counts as weight I, and yi similarly counts as weight I. So now if you look at an expression of this kind, rank f is just an integer. C1f up to Cnf lie in the particular Chow groups. So I think of the Chow ring as something graded, the weights correspond to the degree of the corresponding Chow group. So if I take a monomial in these things which has degree n, that's exactly something like this. It's and if I evaluate that monomial by giving values to the variables as the Chern classes, that's exactly computing some intersection like this. And therefore, each monomial gives me, if I take rank degree of the monomial, I'll get an intersection number, which is an integer. Of course, the polynomial had q coefficients, so I'll get a rational number in there because the monomial will have a coefficient, maybe it has a denominator. And we saw, in fact, 12 and so on. So big denominators grow actually as the dimension grows. So in the end, this whole expression makes sense as a rational number. So that the Hirzebruch-Riemann-Roch theorem will be a theorem of this kind, and it will also tell you what is the polynomial Pn, not by writing it down explicitly. Of course, for n equal to 2, 3, 4, you can write it out. But for a general n, it will give you a recipe in principle to compute it. It will say there's some indirect way, there's some formula you write, take the degree n part of that, whatever polynomial you get, that's the answer. Okay? So that's Hirzebruch-Riemann-Roch. If you've seen the proof of Riemann-Roch for curves and surfaces in Hartshorne, you have to work a bit, and then you could imagine for this you have to work quite a bit more. Hirzebruch wrote a book, in fact, New Topological Methods in Algebraic Geometry, where he kind of set up a whole big complicated machinery and he kind of proved this. And then Grothendieck came along and found a much more general formulation, the Grothendieck-Riemann-Roch, which we're covering in the course, which gives this an easy corollary. It's much easier than what is done in Hirzebruch's book. Of course, Hirzebruch's thing works also for complex manifolds and for certain other things over complex numbers. But even that stuff can be subsumed in this language. Of course, you won't write algebraically closed ground field and so on, but the general style in which you do it that style of argument can be done, I believe, even in the other case. Anyway, so what does the Grothendieck-Riemann-Roch theorem do in the end? Let me just say something about the flavor of the thing without going into details. Then we'll start doing things systematically. Subhasha. So we're still in the introduction. So, Grothendieck-Riemann-Roch it will be some theorem for proper morphisms f x to y or smooth quasi-projective varieties. Actually, you don't need quasi-projective, but then it gets harder to prove the result. There are very technical difficulties. For example, in Fulton's book, he does discuss it, but only, if I remember right, in chapter 18 of the book, and the proof using a higher algebraic K theory and stuff like that in the non-projective case, non-quasi-projective case. The general case, basically what it means is that somehow you have to involve the so-called higher Chow groups in the theory in order to deal with the most general case. Quasi-projective is the case which I'm dealing with in my lectures, and that works fine. It's not so difficult. So whatever it is, it's going to be a theorem associated to, about such morphisms. And fact, such a morphism has a factorization in the following form. This I is a closed embedding. So the claim is that if we have a proper morphism fx to y, it's always possible to extend it, put it into a diagram of this kind, where this map to y cross pn is a closed embedding, and the map y cross pn to y is just the projection. Let me try to explain why this is correct. This is a key fact. I'm using the quasi-projectivity. So what you do is you choose phi x to pn and injective immersion onto a locally closed subvariety. After all, X is quasi-projective. What it means is there is a projective variety and an open set inside it, which is isomorphic to X. So choose one such way of writing X. Choose a projective variety with an open set in it, such that X is identified with that. Okay, let phi be the isomorphism between X and that open set, which I can as well think of the map as values in projective space. Then what you can do is you can take X to y cross Pn, which is the pair of maps f phi, and then obviously this diagram commutes. Right? I mean, it's just saying on the first coordinate take f, the second coordinate take phi, and then near project means I forgot the second coordinate, so I just took the first coordinate, which is f, which I started with. That's obvious. This map is of course injective, because the second thing phi is injective. But in addition, this is a closed, this is a proper map, because f is proper. Anytime you have a diagram like this, if this map is proper, that map is automatically proper. Think of this. This is a part of properness, Archon chapter 2. Right? So now I know this is injective and immersion and it's proper. That's exactly an embedding. So such a factorization always exists because I stuck to quasi-predictive varieties. That's one thing. The existence of such a diagram is just basically saying it's quasi-predictive, all the varieties. Sorry? I used only X as quasi-predictive. That's correct. But in the end, I'm going to prove, well, I'm going to look at the map y cross P into y. I'm going to use y is predictive. I believe. Maybe not. Maybe the argument doesn't matter. Maybe it doesn't use y predictive. Anyway, we'll see. Maybe you're right. Maybe I get by without it. But the image of X inside y is predictive, I suppose. Not clear. Yeah, anyway. Okay, so maybe Nitin is saying some more juice can be squeezed out of the argument. Possibly he's right. One needs to think about it. Okay. Right. And another feature, it will turn out, GRR, in the nature of the theorem, if it holds for Fg, then it holds for G composite F. Whatever the statement of the theorem is, it will have the character. Once we get to it, you'll see it's sort of essentially obvious that it's compatible with composition. Two maps for which it's true, I can compose them. So in other words, if I have a general map, because I can factorize it, it's enough to prove Grothendieck Riemann-Roch path by two different arguments, one for this type of map and one for that type of map. And that's going to be the strategy. And then what is the relation with Hirzebruch Riemann-Roch? HRR is going to be the special case where y is equal to a point. So if you want to prove Hirzebruch Riemann-Roch from this point of view, you have X mapping to a point, but X happens to embed in projective space, and projective space maps to the point. So if I can prove it for the embedding, whatever the statement is, and if I can prove Hirzebruch Riemann-Roch for projective space mapping to a point, in other words, if I know Hirzebruch Riemann-Roch for projective space, I can deduce it for any X. That's what is going to follow with the machine. So that's the way in which Hirzebruch Riemann-Roch's proof got sort of simplified in this machine. It's set up in some fashion, and this embedding also, you will change the embedding to a nicer embedding where it will be somehow almost built into the way everything works. So that's what the notes, my lectures are going to try and cover that. So all this was supposed to be introduction to the subject. Now let's get to the systematic development. Okay. So the first step, as we can see, we need to know about Chern classes. Some theory of Chern classes has been developed, but I want to do things my own way, which are somehow compatible with my lectures, and also I'll use various calculations which will come up in the process. So it's also part of my business. So Chern classes, whatever they are going to have something to do with Chow groups. So we need Chow groups before Chern classes. Chow groups, let's start with that. Let's review some things. And somehow one of the points in the whole Fulton machinery, which is what we are following in this course, I think, hardly, is that even if you're interested in certain specific questions, non-singular varieties, intersections and non-singular varieties, things which you expect to have good properties, in order to rigorously set up the theory and check all the things properly in the most reasonable way possible, it's best to allow yourself certain freedom, try to set up parts of the theory in much greater generality, and then in the end specialize to the cases which you want later on. But in the middle of the proofs, the fact that you set up things with greater generality allows you to bring in, say, singular varieties or non-reduced schemes or reducible things somewhere in the middle of the argument, bring them in, and then in the end you take them away. But whatever, it's good to set up things in greater generality somehow is the point. And somehow the idea would be to see, even if you're interested in a specific application like GRR, all of the various abstract things which were introduced in the Fulton thing will actually get used somewhere or the other. Because we have the freedom to do certain things, we are able to argue a certain way. I'll try to point out one or two places where, and specifically in the notes, one place I've written, this works only because we allowed a more general thing. I specifically put a comment there. Other things occur to me, I'll try to make. And others, of course, experienced members in the audience can similarly comment that this needs this, which we develop, something like that. So, I think we've taken a fairly utilitarian point of view. In spite of trying to write various abstract general things, we're not doing more generality than is really required for the purpose. Not generality for its own sake. Okay, anyway. So now X is quasi-projective, but it's a scheme. So it's reasonable, but it could have non-reduced elements in the structure heap. It could have components, may have things of different dimension, whatever. You can talk about. That's the generality which you want to start. So then we talk about Chow lower px equals Chow group of p dimensional cycles mod rational equivalence, right? That's defined as Z lower px mod R lower px. Right, remember Z lower p is free abelian group on classes V in X irreducible dimension V is equal to P. Of course, though we have a certain level of generality by allowing ourselves schemes and so on, still everything is a finite type over a field, whereas bad things which could happen in the bigger world of schemes, even of Noetherian schemes, those things are not there. All schemes are finite type over a field. So dimension behaves exactly like you think it will behave, no funny things will happen. Your geometric intuition works quite reasonably. Okay, I just want to stress that. So okay, I have this. RPX is cycles in ZP X rationally equal to 0 which is the group generated by things of this form Oh, when I write irreducible, maybe I should be more careful. I should really write integral. Irreducible is just about the topology. Integral is also saying, about the scheme structure. Similarly here. So take varieties W, integral subvarieties W of dimension 1 larger than the number P. Take a rational function on such a W, non-zero rational function, star means non-zero, and then take its divisor. So div f W is sort of zeros of f minus poles of f, right? And this is an element in Z lower px. And probably in Nitin's lectures, it has been defined. This has been carefully studied, and its properties have been established. Notice W is integral, but W could be singular. So when you talk about a function and you want to talk about its divisor, you have to be a little careful, and that care was taken in those lectures, and that would have been done. Okay, so but this in classical algebraic geometry, they kind of swallowed this much, I would say, of the singularities. They were willing to allow this. But when you go further, this additional room here is really from a more modern perspective, which is why the methods, we can give these kinds of proofs, the kind of proofs which we're going to do. So remember that if f x to y is proper, there exists f lower star chow px to chow py, and if f y, let me say g, y to x flat of relative dimension d, there exists g upper star chow px chow p plus dy. So this is called proper push forward of cycle, the first thing, and the second one is flat pullback. So these things keep coming all over the place. We'll always say anything which we set up, we'll try to see how is it compatible with proper push forward, how is it compatible with flat pullback, and then is there any interaction between the two things. So then these are two properties, and then the third property is compatibility. For appropriate fiber squares. So suppose this was proper and this was flat of relative dimension d, then the other two maps are also proper and flat of the same of relative dimension, and I'll leave you to formulate and prove the exact compatibility statement. Let me not say what it is. There's only one reasonable thing you can write down as compatibility, and that's correct.
So give the name push pull.
You already did it? Okay, good. Nitin has solved the exercise for you. I was hoping people will wake up a little bit and try to think about the second one. Right. So this is a compatibility. I'll use this also sometimes. Okay. Another thing is, to set up intersection theory, you start with intersection with divisors, or rather something called pseudo divisors. This is something in between a divisor and a linear equivalence class of divisors. So I believe these things have been kind of concerned, but I'm going to run through some of it again. But the key, one important property of this, commutativity of the intersection, proof left to the previous lectures. I'm not going to do it. It's a nasty, complicated argument. And it's a technical argument, you should check that it's correct, but afterwards you just use the fact, the way I view it. I mean, the proof itself, apart from convincing you that it's all rigorous and correct, I'm not sure right now it's something you need to worry about. I'm going to use it as a black box. So anyway, so I have these pseudo divisors. Let me just remind you quickly what they are. So L is an invertible sheaf, and Z in X is closed. X is a scheme. Huh? Yeah, well. So I haven't said anything. X is a scheme, quasi-projective scheme. And then you have S, a section of L restricted to the open subscheme X minus Z. So S therefore gives me a map from the structure sheaf, the sheaf of functions on X minus Z, to L restricted to X minus Z. Exactly. So part of the data is this is an isomorphism. So this section trivializes the restriction of L to X minus Z. All this data together is called a pseudo divisor. Sorry. I guess that's the reasonable order to write. You have to first given the invertible sheaf and the Z, then you know where you're trying to trivialize it, and S is the trivialization. So this data is called a pseudo divisor. And you write the notation as though it's a divisor. D equals. And the point is, these things have many properties, kind of like we're used to for divisors or non-singular variety. So what are different things, properties of this? If X is integral D a Cartier divisor. Here I should have said there's a notation here for the pseudo divisor. Yeah, it's better to do it here. Support of D, which I'll write this way, is just the same Z. Why bother with the separate notation? But sometimes I may not have given the Z explicitly. The pseudo divisor might have been constructed by some process. There will be some underlying Z, whatever it is. I haven't given it a name. But if I want to talk about it, I just put mod D, and that means the underlying Z. Okay. Okay. If X is integral and D is a Cartier divisor, it has a notion of support in the sense of Cartier divisors. There's an underlying Weyl divisor, for example, and take the support of that. So therefore, there exists OXD and then the same support D and the SD. This is the tautological section. What? Yeah, but I mean, how do I put it? We're not taking the section on X. The pseudo divisor consists only of the section on the opposite. Where it's a trivialization. I don't care what happens on X, on the support of D. I'm neglecting that information deliberately.
I'm simply saying the support of the Cartier divisor.
Yes.
Might be rather than the support of
You're saying I should define the support of the Cartier divisor as the set of points where, no, what is it?
external support of the section of A star not O star.
Mm-hmm.
Where that section is on A star.
That's a reasonable option. Yeah. You're saying it's not equal.
Yeah, I mean, you can have alpha one something like X plus Y, and the weight divisor won't include that one.
Well, it will kind of, but yeah, okay. Nitin is saying we should work more carefully scheme theoretically with the notion of support in the sheaf sense. Technically, what is a Cartier divisor? On an integral scheme, you take or any scheme I suppose, take the sheaf of, K star is the sheaf of total quotient rings of the thing, and then O star sits inside it. Take the quotient sheaf, take a global section. Then, being a section of some sheaf, there's an underlying notion of support coming from topology. Given a section of sheaf of abelian groups, take that thing and call it support. Nitin is correct. So this is the support of D, and calling it the support of A divisor is not correct. So Nitin is okay. Anyway, so the assertion is that if you have a Cartier divisor and an integral scheme, that comes equipped with an invertible sheaf because it's a Cartier divisor plus a tautological section. So indeed you get this notion. Pseudo divisor notion comes from that. That's correct. There's no problem there. Then if X is integral, implies there exists natural map pick X to chow dimension X minus 1 X, which sends the class of OXD to class of associated Weyl divisor. This is okay. Where? Here. No, I'm not assuming it's integral. It's possible, it's allowed. Z equals X is allowed. So then there's empty data of the section. Exactly, it's allowed. It's allowed. And the point is, in the middle of some nasty sort of construction, when you blow up things and do couples, this could happen. The whole notion of pseudo divisor is designed to allow that case somehow.
And to allow the backs, which otherwise.
That's right. I mean, so then when you do various operations, you will end up in cases like the one which Kapil flagged as a pathological case, and the point is you want to allow that too. because that could occur somewhere in the middle of the argument. You don't want to each time argue that that doesn't happen, and that, or if it happened, I can do something. You don't want to get into that kind of mess. The thing is designed to automatically take care of those things. Okay. So this is obvious, right? Okay. So therefore, fine. This is fine as it is. This, if I have a general invertible sheaf, I do have a class in the Chow group of X. But the point is, a pseudo divisor is a little bit before the sheaf. Sort of. Cartesian divisor is the most basic object you can think of. Invertible sheaf is something I can associate to a class of Cartesian divisor. Pseudo divisor is somewhere in between. So instead of just getting a class in the Chow group of X, you can get something better. So that's the point. So if I have D equals L Z S pseudo divisor on integral X, there exists well-defined class of D in Chow dimension X minus 1, but of Z rather than of X. And somehow this is the advantage. The point of working with pseudo divisor is to get this improvement from X to something smaller, sometimes, depending on the situation. Okay? It's important that this is better. Better means it could be better, it depends. Z could be equal to X, that's allowed. But if Z is smaller than X, you got extra information. Yes, yes. You have a local defining equation, etc. And you have many things. Or a pair of such, whatever. You have more information. Right. And then if F y to X any morphism, there exists and D equals L Z S on X, that gives rise to F upper star D, which is F upper star L, F inverse Z, F upper star S. If y and X are integral and D is Cartier on X, then F upper star of O X of D, or I should say O Y of F upper star D. No, I should write it the other way. Sorry. The once X and Y are integral and D is Cartier on X, then of course D also had an associated pseudo divisor. So there's a notion of pullback of the Cartier divisor and the pseudo divisor of that, or pull back the pseudo divisor from below. It's the same thing. That's what this is saying. Okay? So in the special case which you already had of Cartier divisor, where it's more rigid, you have more information, there was a notion of pullback. The notion which we have now extends that.
Sorry, what if the image of it is entirely within the support?
I think it doesn't matter. Can't you still pull back the Cartier? You can't, right?
You pull back the alignment also, right?
No. Can't I pull back the Cartier?
It won't remain a Cartier. It will just be a pseudo.
So you're saying this makes sense,
What makes sense?
and this equal to this is meaningful, whatever that is. but this is a pseudo device. So in other words, here the only thing I can put according to you is this, right? O F upper star OY OXD. Even if the x and y were integral, you're saying y after all maps into d, you have problems with what you're saying. Maybe you're right. Right now, standing here, I can't. I mean, you're probably right sitting there. The person sitting in the audience is more likely to be right in such circumstances. Somehow I thought there was some point here. Anyway, okay. So if xy integral d Cartesian x and f of y not contained in support d. If I had this situation, f of y not contained in the support of d, then I can pull d back as a Cartesian divisor, and then it does make sense to compare the two pullbacks and they are the same. That's the only assertion I can make reasonably.
Then you use the fact that this keeps integral.
Of course, integral is being used in any case, yeah.
And y is also integral.
Yes, everything in being integral is used. So why did we introduce all this stuff and why did I get myself into all this hot water here? Because the point is, this is one case where you want to set up an intersection product which you can write down directly in some fashion. And then try to argue that it has reasonable properties and then build the general intersection theory on this specific intersection class. Okay. So then, as I said, the point about these things is that you can intersect them, intersect cycles by these things, intersect with pseudo devices. Let me just write one or two things down and then stop maybe for today. So if D equals L ZS, so a pseudo device on X, IV irreducible of dimension M, there exists well-defined class which I'll write in this fashion: D dot bracket V in chow M minus 1 of Z intersection. So somehow the point in this whole Fulton business is to first define this, prove its properties, and reduce everything else to this. Okay. So what you do is you take IV upper star of D. This is a pseudo divisor on V, and then you take class of IV upper star, well, with support Z intersection D, of course, Z intersection V. If the ambient thing had support Z, then after restricting, it has support Z intersection V. And then you take IV upper star D and take its associated cycle in chow M minus 1. Z intersection V. Associated cycle made sense because I assumed V is integral. And that was the comment I made here. If you have a pseudo divisor on something integral, because you had a support Z here, there's a class of that pseudo divisor not merely in the chow group of X, but actually in the chow group of that support. So that's what we constructed here. It is in the chow M minus 1, M is the dimension of V, chow M minus 1 of the intersection. So depending on what this intersection is like, this could just be a cycle, because this could be the chow M minus 1 of an M minus 1 dimensional variety. So that's just a linear combination of the components with some coefficients. So that's an actual cycle. Or it could be that there are parts of it which are bigger dimensional, and I mean V was integral, so this could have been the whole of V. Then I would have got a class in chow M minus 1 of the ambient space V, depending on the circumstance. V irreducible. I keep writing irreducible and I should be writing integral. Sorry, whenever I write irreducible, please remind me to write integral. Irreducible is only about the topology, integral is about the scheme. careless.
So you are saying worst case Z intersection B could be V.
Yes, that's allowed. Yeah. And then this has obvious properties. Let me write down 2 to the power and just stop. I'm of course not going to prove anything. I'm just going to state the properties, and they're pretty obvious. D V, the ordered pair dV, pseudo divisor and subvariety, goes to D dot V. This I've deliberately formulated in a somewhat vague fashion. This is bilinear. So now there are various ways you can try to understand what this means. For example, I can keep V fixed and take D1 and D2, then it's pretty obvious what it means. But I can take D fixed and take two irreducibles V1, V2 and take the sum. Of course, I'll define the thing as the sum of the classes, but each one lived in a different place, right? Z intersection. If I have V1 and V2, I'll have something live in Z intersection V1, something else living in Z intersection V2. But then, of course, I can take Z intersection V1 union V2, both those Chow groups map to that, and there it will be, the formula will be cut. No, that's why I put down in quotes. Once I put it in quotes, you have to figure out what is the meaning and prove it. These are the things it's too messy to actually write down all the possible cases, but you can easily imagine what it's supposed to mean. Anytime you have a question of doing it linearly, I mean, take the smallest place where all of the terms make sense. In that group, I have an equation. That's what it's saying. Okay? Some things are better not formulated carefully. People in the audience are fairly intelligent. They'll figure out what's the right thing. So then proper push forward. Property is an obvious thing, and then flat pullback property. So proper push forward property will say what? That will be some kind of projection formula. It will say F lower star or F upper star D. Let me write a version of it. Dot alpha is equal to D dot F lower star alpha in Chow M minus 1 of Z for example. Z is the biggest thing in which everything can live, so for example it's true there. It will be true, I mean if you could improve the Z to something smaller, there also it will be correct, but I mean, I'm just writing typical kind of form. Or this could be something like this, F upper star D dot F upper star alpha is F upper star D dot alpha in Chow M plus D minus 1 of F inverse Z. Something like that. If I have F y2x. In the usual thing. I have a flat map of relative dimension.
First equation, what is Z? It's F of Z.
No, D was below.
D was below.
Z is also below. Yeah.
So the intersection F of Z.
Alpha lives upstairs. Push it down. I could have done better maybe, yeah, but this is also okay. Yeah, I was hand waving saying you can improve it if you can make. I didn't give any details. Yeah. And let's observe one property. This is an important property. It's trivial, but it's important. And then I stop with that, I think. If D equals L ZS, pseudo divisor, and L is isomorphic to OX. Not necessarily with this section, but there exists an isomorphism. And alpha in ZMX, then the claim is D dot alpha equals 0 in Chow M minus 1 Z. Because how did the whole business work? I took my I upper star D in, think of one of the components of such an alpha. It's a V. I took something and took the associated Weyl divisor. But if the line bundle is the trivial line bundle, the associated Weyl divisor is linearly equivalent to 0 in the group of Weyl divisors Monte curves. So the equivalence class is 0. That's what one is saying. It's true for each of the components, it's true for a general cycle. I'll stop with this today. I think this is good.